Hello, I'm Gaurav Duggal, a fifth year PhD student with the Wireless at VT research group at Virginia Tech. This poster presents my research on wireless localization for next generation emergency networks. The central question is, how can we accurately localize targets when direct wireless paths between a transmitter and receiver are blocked? My work addresses this through three fundamental contributions. The motivation comes from emergency response. Accurately locating responders inside buildings is critical, but GPS signals are too weak indoors, making positioning difficult. A promising alternative is to deploy UAV anchors outside the building that transmit wireless signals. Because the building exterior blocks the direct path, the signals mainly enter through the windows. Conventional positioning methods assume straight line propagation, so here they can produce large errors and may even place the responder on the wrong floor. To address this mismatch, the first contribution of my work is a new physics based propagation model. Contribution 1 establishes the theoretical foundation. Here, the direct path from the UAV to the indoor receiver is blocked, while the glass is effectively invisible to the wireless signal. So the signal reaches the receiver by edge diffraction, bending around the window edge before propagating indoors. I derive a new model for the length of this bent path from the first principles of electromagnetic field theory, and then derive the fundamental limit on localization accuracy. A key feature of this model is that it's symmetric in x and y coordinates, but asymmetric in the z coordinate. That structural insight directly leads to contribution 2. Contribution 2 is a low complexity localization algorithm for estimating the position of an unknown target, here the responder. Under the diffraction based model, this means minimizing a cost function over the unknown 3D target position, which leads to a non convex optimization problem. Solving it directly would require a dense 3D search, which is computationally expensive and not guaranteed to find the global minima. Instead, I exploit the horizontal symmetry of the model. For each candidate height, I solve for the best horizontal position and then perform a one-dimensional search over the height to recover the final 3D estimate. The plot shows that even this one-dimensional cost has two local minima, reflecting the non-convexity of the original problem. But in one dimension, it becomes much easier to identify the global minima corresponding to the correct position while achieving major computational savings. Contribution 3 focuses on optimal placement of the localization infrastructure. The photographer analogy gives the intuition. If all the photographers stand too close together, they get redundant shots. And if that viewpoint is poor, all the photos may be poor. The obvious fix is to spread the photographers around the subject to get more diverse views. But that leads to a chicken and egg problem. How do you place them around the subject if you do not know where the subject is? Classical anchor placement also suffers the same issue. It assumes the target location is already known in order to place the anchors optimally, even though localization is meant to estimate that unknown location. My work resolves this by extending the notion of optimality from a single point to an entire indoor region. So the anchors are placed to maintain strong localization accuracy across the region, not just one location. The first simulation plot evaluates the localization algorithm. The x-axis is the signal strength, and the y-axis is the positioning error in meters on a log scale, where lower is better. Across a range of signal strength, the proposed method reduces positioning error by about 35% relative to prior methods. At moderate to high signal strengths, it it also reaches the fundamental limit, showing that the algorithm is both computationally efficient and essentially optimal in that regime. The next simulation plot focuses on anchor deployment, comparing average positioning performance across different UAV deployment strategies. The two placement algorithms from my framework improve performance by about 18 to 30% over three benchmark strategies. Taken together, these results show gains at two levels: better position estimation and better UAV deployment. As future work, I plan to build a wireless localization testbed and validate these results in the field. More broadly, this work shows that diffraction can be modeled and exploited as a useful source of information for accurate indoor localization. Thank you.